All right, Advent of Code day 14. What do we got? Another grid. Rounded rocks. Tilt. What? Okay. I see. $118. Sure. 2. North, west, south, east. Huh. Seems like a lot. Let's see, we just need to rotate it, right? doing? Okay. Okay. All right. So what was going on here? This doesn't feel like it was the nicest. Also, I don't really have a solution to part 2. Anyway, so we're given another grid. It's been a lot of grids lately. This one has 3 characters in it. So it has dots, it has hashes, and it has O's. So dots are empty, hashes are walls, and O's are rolling around the grid. So in part 1, we were asked to roll everything north. So everything just, let me just print this out. So t is 1 and j is 0, print score g. That work, 107,430. Cool. Okay, so we were asked to roll everything north. So you can see, like, these 4 rocks, they start out with an empty space that gets compressed. If you have 3 rocks in this column, it's all otherwise empty, they get all compressed. This one, they can't roll past this hash sign, so you get 1 up here and 2 sort of lined up here and so on. So then we're supposed to do that and then count. Every rock gets scored based on its row index. The top is the highest. So rocks down here get 1, 2, 3, so on. So we can see I've defined, well, for part 1, there's 2 relevant functions, which are roll and score. So roll takes in a grid and then rolls the rocks north. Pretty inefficiently, but that's fine. Maybe I'll clean that up. So we just do each column independently, right? Because they're only rolling in one direction. The columns are all separate. And then for each row, like basically if the rock can roll north, then roll it north. This is, and then this only moves rocks, sort of scanning from top to bottom. This only moves rocks like 1 square north for a scan. So we need to do our scans, right? If you imagine a rock that started at the very bottom, like on the last iteration of this loop, it will move north 1. Presumably there is a way to improve that. If you go bottom up, you get a similar problem. Like if the row is all rocks, then only the top one moves each time. So I'm sure there's a way to do this all in one pass. But I'm not sure what it is. I mean, that's not true. Like, you can just sort of keep track of how many rocks you see until you hit a hash sign, and then move all those rocks to the top. But that just seems more complicated. Okay, so anyway, I have this very inefficient method of rolling to the north. It works. It also modifies the input array, which is ugly, but again, it works. And then scoring is pretty straightforward. Just go through all the cells. If you see an O cell, then you get scored R minus R. Oh, interesting. Yeah, I really should have been more careful about this. Wait, what? How does this even work? The point is, in part 2, like, the grid is rotating, so you need to be cautious about just reusing like R and C from the original grid. But okay, fine. So fine. So, first so for part 1, first we roll them all north. Really, this maybe should be called roll north. And then we score it, which is just everything scores, like the first row scores the number of rows, the second row scores the number of rows minus 1, and so on. So that's part 1. Part 2, more complicated, says first we're going to roll north, then we're going to roll west, then south, and then east. And we're going to do that 1 billion times? 1 billion times. It's a lot of times. What is the final score after doing all that? Okay, so first let's talk about the northeast, northwest, southeast, northwest, southeast. Then let's talk about the billion. Basically, I think we need to handle them separately. So I figured, okay, well, I already wrote a roll north function. Let's just reuse that. We just need to spin the grid around 90 degrees, and then, if we spin the grid around 90 degrees and then roll north again, that's the same as rolling west. So that's how I've handled the rolling north, west, southeast. It's just always roll north, but then rotate the grid around 90 degrees. And hopefully after 4 rotations, it's back where it started. Here is rotating 90 degrees, which I got lucky on, basically. So this involves transposing the grid. So instead of R rows and C columns, you now have R columns and C rows. Hopefully that makes sense if you flip it 90 degrees. And then also, like each cell in the cell in the original grid gets mapped to like the rows and columns switch places, and one of them gets inverted. And I sort of just randomly picked or guessed that the row should get inverted. I think it, like which one gets inverted just affects which 90-degree rotation you get. And so like one of them is going to give you north, east, southwest, and one gives you northwest, southeast, and I kind of got lucky that the first one I tried gave me northwest, southeast. So fine. But yeah, that's 90-degree rotation, is just swap the coordinates and invert one of them. And I don't know, if you think about it, if you do this 4 times, you'll have like swapped them 4 times, which is nothing, and swapping 2 is in fact nothing, and then inverted each of the coordinates twice, which is also nothing. So you get back where you started, which is how it should be after you rotate 4 times. Okay, so that's how you handle northwest, southeast. How about handling a billion? So I figured, hopefully there's a cycle here. So like maybe some, the rocks are rolling around at the beginning, whatever, but eventually they probably get into some kind of pattern where they just keep repeating. And that's what I did, is look for a pattern. So I just kept track. This is gross. Kept track of the score after each sort of, 4 rotations, each cycle, and printed out sort of on which time steps I got each score, and tried to look for a pattern. And if you do that, you will see that there is a pattern. In my input, it seems to go by 9s. But I mean, you can see maybe some stuff was happening at the beginning. It's different. Like, I don't know, this one, 3, 14. But eventually it settles down into a pretty clear pattern of going by every 9 cycles, you get a repeat. So then I figured out, like from here to here, it just always keeps repeating, repeating, repeating. A billion is going to land sort of in one of these repeats. So figure out which one it is. So let's systematize that a little bit. Say 5, I don't know, sure. So if we've seen the same score a bunch of times, hopefully we're in the cycle by now. So the cycle length is the difference between the last 2 times that we've seen it. Is this even guaranteed to work? I mean, not really. You get the same number in the cycle multiple times. I don't know, man. Probably a real cycle in that case. I mean, this is still bullshit, but it's close enough. Maybe like this. Nine 0.6317. Well, that's something. Okay, so what did I do here? So I say if we've seen this same score a bunch, and this part obviously is kind of fake. I've just picked some like random numbers that are not, I don't know. I think if these numbers are like big enough, it's sort of guaranteed to be fine. But what if my cycle was length 20 and it had the same number 15 times and then a different number? Well, then this doesn't work. But I don't know. There's still a cycle. Okay, so fine. With that caveat out of the way, I'm not really sure how to fix this in like a satisfying way, so I'm just gonna do this, I guess. So if we've seen the same number a bunch of times, figure out how long we think the cycle is, and like, I don't know, double check that maybe we didn't see this number twice in the cycle. Figure out how many times you can repeat this cycle before going over 1 billion. And just pretend that we repeated the cycle that many times, right? Which will change nothing. We're sort of assuming that the grid is the same. I mean, really, that's what I should do, is keep track of what the grid. Sure. In fact, maybe that's so much more compelling that I will actually do that. It seems a lot less bullshit. I think this is going to complain. Yeah. Okay, fine. This is a lot more principled. We keep track of like what the grid looks like after n cycles. If we see a repeat grid, then we know that we actually have a cycle, and we can just keep repeating. We can sort of increment. If we do that many cycles again, we're going to get the same grid again. So we just keep doing that as many times as we can to stay under 1 billion, and then just like increment our time counter by that amount, and then let it sort of finish off the billion. So, let's just like print out which values of t we actually end up evaluating. So we evaluate 102 time steps, then we see a cycle, then we jump all the way to 999,999,994 and evaluate the last 6 time steps, and then we get our final answer. So we know what the grid looks like after 1 billion time steps, but we only ended up evaluating like 110, 108, I think, to get our answer because of this giant jump with the cycle. Cool. So that is it for day 14. See you tomorrow.